Hello, and thank you for attending our webinar. Today, we're going to talk about UV and all-wavelength collection and how to get the most from your system. We will discuss optimizing UV absorbance for both maximizing the detection and also preventing peaks from going off scale. We'll discuss all-wavelength collection and how that can help you. Then we'll go over into ESLD, evaporative light scattering detection. Have a quick overview of that, and we'll show how to handle semi-volatile compounds and maximize the response from these compounds. We'll talk about setting up the ESLD for different solvents and the advantages of temperature control. The first thing we're going to talk about is the UV spectrometer. You can measure the absorbance on a UV vis instrument. If you do so, remember ionizable compounds can change their UV absorbance. Look for ionizable groups near conjugated double bonds and aromatic rings. And check the UV, preferably using the modifiers in the mobile phase. Also, running a fast scouting run allows you to see the UV absorbance on many instruments after the peak elutes. For this first peak, I would select this maximum at 260 nanometers to maximize the peak sensitivity, and a wavelength on the shoulder to keep the larger peak on scale. We want smaller peaks larger to maximize compound recovery, while keeping large peaks on scale allows us to verify a single component only is eluting. TLC plates are infused with zinc silicate, which absorbs at 254 nanometers, hence the name F254. After it absorbs the light, it then emits a green light. For fluorescence to occur, there has to be an absorption of light. So therefore, if the compound blocks 254 nanometer light, this light can't get to the phosphor, and there will be a dark spot because there is no fluorescence. If you synthesize the compound, you can calculate the absorbance maximum. There are several sets of empirically derived rules which predict the wavelength of the absorption maximum in an ultraviolet visible spectrum of a given compound. I have included a link to one of them, but it's easy to find this online. Here are a couple of examples. Heteroannular means the conjugated bonds are on two rings, while homoannular double bonds are on the same rings. The table shows how you add and subtract various numbers to get a UV absorbance maximum. If your compound has absorption from 200 to 225 nanometers, you can replace ethyl acetate with acetone. They are in the same solvent selectivity group, and acetone is miscible with hexanes also. This chromatogram is para-nitroaniline and 3,2-nitrophenylaminopropionyl made from the para-nitroaniline. Detection was at 210 nanometers in a hexane acetone gradient. You can see that the baseline remains nice and flat. Another way of detecting peaks is with the use of all-wavelength collection. All-wavelength collection looks at the shape of the UV spectrum as the chromatogram progresses. This is done by converting each wavelength to a vector. The length of the vector is the intensity at a given wavelength. The wavelength is represented by something analogous to a direction in space. Each absorbance scan, all of the wavelength absorbance vectors are combined into a single vector. Each compound has a unique composite vector, and a change in vector angle represents a change in the shape of the absorbance, and therefore it represents a change in either the compound or an impurity eluting with the compound. T0 is measured after the equilibration on teledyne ISCO systems before the compound dilutes. T0 is the base transmission. The transmission is also measured during the run. Absorbance is calculated from the transmission data. If there is something in the flow cell at the start of the run, T0 will be less than 100% transmission. The range of absorbance that can be detected at that wavelength will be reduced, and this is important when we discuss absorbing solvents. When a UV detector is saturated, that means the sample blocks the light, and therefore no light gets to the detector. If the solvent blocks the light at some wavelengths, the absorbance is also reduced. With all-wavelength collection, we can see changes in the parts of the detector that are receiving light that are not blocked by the solvent, and we could collect on those changes. The signal gain is used for all detectors on the teledyne ISCO system. It simply multiplies the signal from the detector by the value shown in the gain. The wavelength range is used to set the wavelengths used to detect compounds. It can be changed to encompass the entire range of the detector or set to a smaller range to exclude known impurities. Enabling baseline collection on next-gen 300 and 300 plus systems cause it to measure the solvent baseline within a gradient before a run starts. This eliminates baseline drift and improves the sensitivity of the all-wavelength collection for compounds run with solvents that absorb light. When working with non-absorbing solvents or when using a wavelength range when the solvent doesn't absorb, this can be turned off. Here, a porphine compound was synthesized by a Rothemund reaction. Porphines also have interesting optoelectronic properties, so they are used for electronics and optics. They are also used in fluorescence-based sensors, and they can coordinate metals for catalysis reactions. Being aromatic, they elute in a hexane toluene solvent system, and also being aromatic, the UV spectrum is similar to that of other aromatic compounds. All-wavelength collection allows detection of the compounds. The steps that you see are due to detection of slight differences between the compound and the solvent system used to elute the compound. Toluene has a strong absorbance from 200 to beyond 280 nanometers and a strong fluorescence emission into the visible region. The UV lamp causes the excitation. So the absorbance and emission are not linear when run in a linear gradient. We measured the absorbance spectrum with a gradient outside the column before the run. The spectrum is made more complex by the inner filter effect, where the sample or the solvent absorbs all the light and limits fluorescence, so the detector doesn't get any light. When I say limits fluorescence, I'm talking about the toluene emission. The fluorescence actually goes down as you go into the gradient. However, when you run a sample, the inner filter effect also blocks the light from the detector. In any case, the combination of absorbance and emission changes as the solvent composition changes. Other instruments are unable to detect such compounds in absorbing solvent systems very well. Some systems will simply subtract the solvent from the chromatogram, and when you get a saturated system, it can't deal with detecting a compound very well. In this case, the system doesn't subtract it off, but it tries to measure the absorbance. The detector, being light limited, has baseline noise, and the baseline changes with the solvent composition. Another way to detect eluting compounds is with evaporative light scattering detection, termed ESLD. Compounds with no or weakly absorbing chromophores can be detected. It can be used if the sample and solvent absorbance overlap. A weakness is that volatile compounds can be difficult to detect. Compounds liquid at room temperature are often missed by any ELSD, no matter who makes it. For the ELSD to work, a portion of the column effluent is nebulized. The large droplets are removed because they won't evaporate quickly. The solvent is evaporated, and the particles that are remaining are detected via scattered light. Compounds with no absorbance can be detected, such as sugar compounds. Also, compounds whose absorbance overlap the solvent absorbance, and compounds with weak absorbance, such as tocopherols, have increased recovery with ELSD because we see more of the peak. All ELS detectors divert part of the aerosol cloud to accommodate the high flow rates and mobile phases common in LC. Teledyne's patented thermal split technology has the ability to vary the split ratio smoothly over a wide range. This precise vapor phase control combines a gentle bend with a temperature-controlled spray chamber. For easy-to-evaporate mobile phases, the spray chamber walls are heated, and as the aerosol traverses the chamber, it partially evaporates, shifting the particle size distribution low enough so essentially all the particles can negotiate the bend. For difficult-to-evaporate mobile phases or high flow rates, the walls are cooled. When the aerosol exiting the nebulizer encounters a cooled environment, it partially condenses into larger particles whose momentum carries them into the wall and down the drain. By making the walls cold, a portion of the vapor phase is diverted away from the evaporative zone. The ultimate benefit of thermal split technology is that it can be controlled in a smooth analog fashion by simply controlling the temperatures. The temperature of the nebulization zone can be set from 10 to 90 degrees in 1 degree increments. This achieves split ratios from 99 to 1%. Unlike some ELS detectors, our splitter isn't only on or off, it can be fully on or off for anything in between. This is exclusive to Teledyne ISCO products. If a droplet from the nebulizer contains anolyte, when the solvent evaporates, there will be a dried particle of that anolyte. If the droplet was just solvent, it evaporates to nothing. If we shine a laser at that dried particle, it will scatter light. The scattered light can be measured with an electronic eye. Teledyne uses a photodiode for good dynamic range. The electronically amplified scattered light then becomes a peak on the chromatogram. Using the ELSD settings, the default settings will work well probably 99% of the time. You get good recovery and the peaks are on scale. Sensitivity is an electronic gain, and you set it for normal phase and high for reverse phase. Teledyne ISCO columns have RFID tags which allow the system to set this parameter for you, and you can also set it for high with solvents with high boiling points. Signal gain is a multiplier. The signal and any noise will be scaled, but it is a fast way to improve sensitivity of small peaks. Scaling is increasing the gain to improve the response of weak signals. Setting the spray chamber temperature is a way to send more sample to the drift tube. However, setting this too high will cause baseline noise because large droplets, which may not have time to evaporate, also go into the drift tube and past the detector. This can be reduced by setting the drift tube to a higher temperature. The spray chamber and drift tube settings are different for normal phase and reverse phase, but the system sets them when you choose a column or when the system reads a column RFID tag. You can also save these parameters when you save a method, or you can open an old run and extract the method parameters. Here is an example of how the spray chamber and drift tube controls can improve sensitivity. This is a semi-volatile compound, and by changing the spray chamber, increasing that temperature, we send more sample to the drift tube, and then we evaporate at a slightly lower temperature to keep the compound from evaporating too quickly. By doing this, we see increased sensitivity and more compounds. We see an impurity now that we didn't see before. I prefer to set the spray chamber and drift tube temperatures before using the gain or sensitivity controls. Both runs in this slide use the same sample. The mobile phase was hexane toluene, high boiling point. In the CombiFlash Next Gen, we could adjust the spray chamber, drift tube, and gain to get a nice clean run. The Next Gen has a smooth signal and can detect an impurity eluting late in the run. A competitor system that does not have this control gets a signal with a relatively low response. Changing the settings greatly improves sensitivity and recovery. This is a scouting run used to determine the focus gradient used for some of the runs in this presentation. We only used a small amount of sample, and of the compound, of the sample that we loaded, only about 20% was the desired compound that eluted from the column. These Rotherbund reactions have pretty low yield. Applying the optimized settings to the focus gradient worked well. ESLD and all-wavelength collection work very well together. I thank you for attending our webinar, and if you have any questions, we can take them now.
Hello, everyone. Thank you so much for attending today's webinar. If any of you have any questions for Jack, please submit them under the Q&A function within Zoom, and he will respond. Hi, Jack. It doesn't look like we're receiving any
right here.
questions. Okay, perfect. Would you like to share some of the earlier questions we had at the European webinar?
Okay. The first question that we had was, if you're running heptane, what would be a good setting be? And settings that would be useful for that would be similar, I think, to the toluene. And we'll be running that very shortly. But going back to that earlier, the toluene settings that I used for a spray chamber was 50 degrees, drift tube was 90 degrees, and since I was still using the thermal split with that high boiling solvent, I had to increase the scaling on that to work. I do have a question. Could you tell more about slope detection on the CombiFlash? What that does is we measured the baseline, and if the baseline changes, that's indicative of either a baseline drift or an actual peak. What we do with the slope detection is there are settings inside of there, and if you set the slope detection to a smaller value, that makes the slope detection less sensitive. It seems kind of counterintuitive, but think about a peak that is very, very narrow. The peak might be 1 or 2 minutes long. What happens is that the slope changes very, very quickly. Whereas if you set the slope for a longer time, that suggests a wider peak where the slope changes very slowly. So that's how you set the slope detection. If you think you're going to have very narrow peaks, you set the slope detection to a smaller number in the method editor. If you take a look at the different size columns, you see that we change the slope settings with the column size because smaller columns tend to have narrower peaks. The next question is, once we select solvent absorption options before the run, can we change the gradient during the run without affecting the background solvent absorption? The answer is yes, you can, because we measure the solvent across the entire gradient range from 0 to 100% B at the start of the run. And if you change that gradient during the run, the system will note that the solvent is now at a different percent B, and then it will then use the background subtraction appropriate for that percent B. Another question that I had was that will the ELSD help me if two spots are co-eluting on my TLC plate? And the answer to that is no, it really won't. What happens in the TLC doesn't affect what happens on the instrument. And I would suggest that you would run a different solvent system to try and resolve those two spots. What you can do is run a quick scouting gradient, as I did in the slides, though, and you could see if there are compounds invisible to UV that are eluting that you might see with the ELSD.
Okay, Jack, we can leave it open for a few more seconds. If there's any further questions, please submit them through the Q&A.
Actually, we do have a couple of more questions over here. Can I speak briefly about the background solvent subtraction? First off, it isn't really a subtraction per se. There are some competitor instruments that simply do a subtraction. And what happens is that the peaks don't show up very well because the wavelengths that are overlapping the solvent are essentially, as I described in the webinar, saturated. But what we do is we do the vector analysis and we measure the vector from the solvent during the pre-run when we measure the solvent UV, and then we store those vectors, and then we correlate, we then compare that during the run to the vector that we measured earlier, and anything different has to be sample. Is there any correlation between molecular weight and ELSD sensitivity? We notice some smaller molecules with no chromophores aren't detected in some cases. The answer is, to some degree, there is. Small molecules tend to be somewhat more volatile. And we find very often that if the compound is liquid at room temperature or has a very low melting point, it tends to be difficult to see on ELSD. And what you might have to do is maybe raise the spray chamber temperature just a little bit and lower the drift tube temperature a little bit. And then maybe you can see that. The other thing that tends to make it difficult to see some compounds is if they're very symmetric. Compounds such as adamantanes tend to be very, very symmetric, for example, and they are more volatile than their molecular weight would suggest. So if you have a molecule with a high degree of symmetry, it actually has a fairly low vapor point compared to other molecules of the same size.